Okay, so good afternoon, everyone. Today, we would like to give you a presentation about what we are working with 3D printing for concrete in Vietnam Institute for Building Material in Vietnam. So in the presentation, I try to bring to you 5 contents. The first one for some very short introduction, and then I will move to the second content with design and fabrication of 3D concrete printer in Vietnam. And the third part will be high performance concrete for 3D printing. The fourth content is some products we print from our 3D printer using the high performance concrete. And also the last, we have some concluding remarks for discussion. A very brief introduction. So where we are from? We're from Vietnam Institute for Building Material under the management of Ministry of Construction, and the head office in Hanoi. And we also have a southern branch in Ho Chi Minh City. And we also have a lab site in Hà province, about 1 hour driving from Hanoi, our headquarters. So VIBM, Vietnam Institute for Building Material, founded in 1969, and we are National Science and Technology Research Institute in the field of building material, construction environment and infrastructure. And we actually assist the state management and national-wide development of building material industry, construction environment infrastructure for the Vietnam government, and so directly for the Ministry of Construction. So concrete research is one of our key research area. So basically 3D printing is an additive layer-based manufacturing technique, and you might already know some very basic steps for 3D printing. The first is 3D modeling. Objects are designed using 3D modeling software. It's very popular now. Then it needs to be format as STL format, giving information on coordination and boundaries. And then it should be slide to layers with same height, and then converted to Z code and transfer to printer for printing the material. And the material is should be high performance concrete, extruded and bonded in layer to form the object component. And now the house. Right, so 3D concrete printing, in our view, it should be the combination of the architecture functional design with high performance concrete, and we use the mechanics and automation control substance 3D printer. And actually, with myself, I joined Loughborough University over 10 years ago, and we print the first bench in the world. You can see on screen with our research team, not 10 years ago. Recent research, basically, when some very early stage of research, I joined Loughborough University, and we did a lot of tests with 3D printer. That's a 3D GAN3 printer. It's also very first printer in the world. And we published some very key papers, journal paper, like development in construction scale additive manufacturing process, and the mix design and fresh property for high performance printing concrete, and also hardened property for high performance printing concrete. Is I just show you the graph here, and also the citation of our journal paper. You can see over 10 years, the first paper now nearly 1,000 citations, and the mix design fresh property high performance printing concrete paper now nearly 800 citations, and the hardened property paper also have been cited over 600 times. And we found that about after 5 years of publication, 2012 and up to about, I think, 2016, 2017, not many citations for the paper, but suddenly, near very recent years, about, let's say, 5 years, the citation number of paper increased very, very significantly. And you can see also the graph I show you here, the number of the research projects in the world come from many countries in the world, and it also went sharply from recent about 5 or 6 years. You can see on paper, because the very first is the contour graphing by 2000, and Loughborough University with concrete printing about 2008, 2012, and after that we have some research center in Europe, Zurich, Delft University, USA, and China. And recently, we found very interesting about the research outcome from Japan through the presentation, the last presentation. So we can think very positively, very potential, and it should be. We feel that it very recent application for the real construction in the very short, in the coming time, hopefully. Okay. With Rust in Vietnam, Vietnam Institute for Building Materials, we also work with some university like Hanoi University of Civil Engineering, and also another university, the Technology University in Hanoi called Phenica, and we try to design and fabricate a 3D concrete printer, the very first in Vietnam. And we agree with each other that some key points for designing concrete 3D printer, it should be a large 3D printing system using dry system control to position the nozzle according to the X, Y, and Z coordinates. And using concrete 3D printing technique by extruding cement concrete material through nozzle to print concrete layers by layer. This type of design is basic design, simpler, more powerful than other options, and easy to manufacture, select locally available component, and it can reduce the cost when building a larger scale rather than robotic arm. We understand that the robotic arm, where some research center use, is very precisely, but we grab about the scale. With the robotic arm, we find hard, inconvenient to print the larger scale construction structures. So we go with the 3D gantry printer. This is what we build, fabricate our printer in Vietnam. So we can see here, we use a printer with the X, Y, and Z, the cast coordinates. And the X-axis assembly has a stroke length 1.8 millimeter, 1.8 meter. The Y-axis 3 meter, and the Z-axis is 1.8 meter. And the printer is driven by servo motor with rotational speed control. And we can see on the screen that we design ourselves a nozzle component, including some part, assemble each other, and use the auger system in this nozzle. And the auger driven by a servo motor as well. And with that sort of system, we did assembly, and we have the 3D printer. You can see this is a real one. This is the real one we complete last year. Yeah. And The printer, the nozzle connect with a concrete pump through a soft pipe. And we also can control the concrete pump to pump concrete, fresh concrete to the nozzle directly. And we also have a control box with our software developed. And so there are some available software in the world. And we start to design component and we print some component. Now we move to the second part to introduce about the high performance concrete for 3D printing. We use some sort of very available normal raw material, including the cement, cement PC40, and we also have triê PC50. Different from other countries, like Europe, you use 52.5, but in Vietnam, 50 and 40. We use a sand with a maximum size 5 millimeters, and we also try a lot with the maximum size 2.5 millimeters. We also use silica film, we use fly ash, what is a very large volume in Vietnam market now. And chemical, we try some different amateur, but we came up with one of the Sika amateurs. So the mix proportion optimized based on some very basic criteria: workability, the open time, strength, the extrusion, the durability. If you have read the paper we published 10 years ago, we define what is buildability, extrudability, and open time. And we all know that the 3D concrete is a really challenging sort of concrete because it should be very good in a fresh property for extrusion, and but it needs to have good buildability. What we define that to build as many layers as possible. In an open time, we need to keep the fresh concrete as fresh as possible. Very basic measurement is we test workability and we need to test it after time interval to know how many minutes, how many hours it can keep the fresh property. And this series of tests, we try to optimize with different silica film content, the fly ash content, the water by the ratio content, the water by ratio, the aggregate by the ratio. And we also vary the extrusion speed and the nozzle speed. And actually, in our test, we also use different nozzle size. But in this presentation, I just concentrate on present you about the nozzle with a 20 millimeter diameter size. And we use a different size, as I mentioned before, 5 millimeter in maximum size, and we also try 2.5 millimeter. So basically, we work with the final, the optimal one, we use a 2.5 millimeter size sand, because actually the 5 millimeter size sand it get a number of difficulties in printing. The strength target was 50 megapascal. So the method of research here, we do a lot of buildability tests. And first of all, we use a motor, a small motor with the compression machine. So we use this equipment we develop ourselves, and we design, we fabricate in BIBM with the piston system. And that's a simulation system consisting of a compressor and a piston to test the buildability. And we did a lot of different mix proportion for optimization. We mix this, we measure workability, Then we put in our measurement system for buildability. This is a piston system, a small piston. The workability, we test with different mixed water bioratio 0.2035 and 0.40. Sand bioratio vary at 0.67, 1 and 1.5. And we test the workability and we measure after 60 minutes, and we found that a number of different mix decrease the workability after time. For extrudability, we try to optimize by variation of speed of the nozzle, 40 millimeters per second, with extrusion speed 40, 60, 80, 100, 120, 140, 160, 180 millimeters per minute, with 20 millimeters per minute interval. The nozzle diameter we test using 20 millimeter diameter, and you can see here the extrudability. Some mix not really good, and finally we find some mix has had good extrudability. And the extrusion speed should be 100 to 140 millimeters per minute. The buildability, with different mixes, we have a different performance of buildability. And you can see on the screen different sand binder ratio, different buildability performance. And it seems that with the water bioratio, higher water bioratio, a bit better buildability. But it also, we understand it depends on also other factors. So the higher water sand bioratio, the better buildability. The higher water bioratio, the worse buildability. Just in general. You can see a very short clip to show we test our ability with only one single layer. One single bit, and it can build with different layers, using different mixes. So the buildability actually with water bioratio 0.35 mix also have good buildability, but it's not really smooth surface of filament. With 0.40 quite good buildability, and smooth surface for smooth surface of filament. So we select water bioratio 0.4 for tests in the real printers. And also, as I mentioned, we vary the ratio of the sand and binder, and we also found that they also have a quite good buildability, but lower sand binder ratio have a good binding between filament and smooth surface of filament. So we use actually the big printer for printing a number of blocks like that for test different direction of the concrete printing. Here is one of the block we print using our printer. And after being printed, the block was cut to make a number of queues and beams for compressive strength test and flexural strength test. And we also print a number of blocks, and we cut it to make some sample for bond test. So we try to apply the tensile load to determine the bond strength between layers. We also print and measure a number of specimens for drying shrinkage. So we can see on the screen the Q, the beam, and also the tensile, the bond strength test with the specimen shown in the lower right corner pictures. Right, so the reason with compressive strength, we also compare with cast specimen. You can see here with the different graph, 3 days compressive strength, 7 days compressive strength, and 28-day compressive strength. And the printing direction really influence on the compressive strength. And we found that the compressive strength in x-axis specimen is the lowest one, and the y-axis and seem better compressive strength, and the z-axis also quite is higher than the x-axis specimen, but at 28 day finally it's lower than the y-axis. So the comment here is the compressive strength of printing concrete. We found just about it's vary from 30 to 60% that of casting specimen, and the compressive strength is X direction is lower than that in Y and Z direction. Quite similar. Quite similar ratio of test result with flexural strength. This is without fiber, and we also measure the flexural strength of 3 days, 7 days, 28 days, and we compare the printed specimen and the cast specimen, and we found that flexural strength of 3D printing concrete without fiber is equal to 30 to 40% that of cast specimen, and also the flexural strength in the X direction is the lowest result. With the fiber, we add the polypropylene, micropolypropylene fiber, and we found that it improved the flexural strength in 3 days, 7 days, and also 28 days. And the flexural strength of the fibers printed specimen improved to, and it's equal about 50 to 70% that of cast specimen. And we also measure drying shrinkage and compare the printed specimen and cast specimen, and we found that it actually quite similar result up to 28 days. And when we add fiber 0.5% and 0.7%, the drying shrinkage improve. Yeah, that means the value is lower than the non-fiber specimen. So we have a printer. We also have the high-performance concrete. Then we did a number of printing with different products. The first one, we tried with the curvy chair, and we were successful with printing this curvy chair. It's just one single bit. So actually, it's not strong, really strong. Yeah, so that's just model to show how our printer can work for the curvy object, like a curvy chair here. And the size is the height is 1 meter, and the width, the wide of the chair is 0.65 meters. Um, and we move to another more complicated shape objects that we print. We try to print a curvy gas and table with a size of 1.9 by 0.7 by 1 meter. And this you can see here, we did 3D modeling. Then we slide the object to our website software, and then exported as a Z-code file for printer. And so we complete the printing of this curvy chairs and table, and it's strong enough, and carry 2 persons at the same time, and it now in IBM. Hopefully one day some of you visit us, and you can visit on site in our institute. Okay. And after that, we try to build a bigger one. This is a sentry box, 2.6 meter high, and 1.8 by 1.8 the plan. And we had a lot of discussion about how to print that with our printer. Actually, we can print one shot for the whole sentry box, but it's really hard to move it out of the printer. So finally, we made decisions that we will print 3 different components, and we would assemble them each other. So this is the first component we print. Show you on the screen. It actually quite curvy behind in the half of the sentry box cross section, and the wall you can see here a lot of void. And we print the 2 sides of wall, and we print the zigzag filament inside of the wall. Anyway, I will show you later on a short movie about how to print, how to design and fabricate a printer, and also how to print some components. You have more understanding about what we have done. Okay. So this is some pictures so you component we print. This picture to show you how we move 3 different components outside of the laboratory, and we did assemble 3 components. And the high performance concrete, so that strong enough. Even the component you can see here, it could be moved and rotate outside of the lab, with a very simple cable and crane, the crane motor, and we were successful in assembly 3 components with each other. Here you can see the complete sentry box. That's what we did in IBM. Anyway, okay, I will show you a short movie about what we have done, and maybe you have more understanding about what we have short movie here. It's a Z-axis design. It's an X-axis with the nozzle mount on the X-axis. It is a yes, it's a nozzle design. It's a nozzle mount on the X-axis. This is a control board design. Frame fabricated in workshop. It is a testability system testing. It assembly between the curvy chair with one socket here. See the concrete print smoothly. It's a fiber concrete mix. Okay, so that's I think the content we show you, and now come to the concluding remark. Yeah, in our research, a 3D concrete user XYZ decaf gum 3 printer has been designed and fabricated successfully with overall dimension 4.9 by 25 meters that can print objects with dimension up to 1.8 by 2.5 meter. High performance concrete having good lecturability, durability, open time, and over 50 megapascal compressor strength, and also over 8 megapascal pressure strength. Less than 0.2% drying shrinkage have been developed, and it can be usable effectively for 3D printing. And the material and the printer has been deployed to print successfully some architecture object, set of curvy table and chair, and a sentry box. Okay, that's it. Honor I bring to you in the second ASAP's webinar